Welcome back to Nick's Algebraics. With me today, I have a random guy,
It is I. I'm back for another banger video.
and we have two special new guests, Paul and Pschilli.
Hello. Howdy.
As usual, the blank and filled out guided notes will be in the description, so you guys can check that out if you're interested. Today, I'm going to talk about some introductory physics concepts, namely displacement, velocity, and acceleration. Let's start with displacement. Does anyone know what displacement is?
Yeah, well, it says on the notes.
Yes,
It's the change in position of an object, delta x equals x2 minus x1.
exactly. Good job. Basically, it's the difference between the object's final and initial positions. X2 is the final position, and X1 is the initial position of the object. So the displacement is just the change in position. It's just delta X. And displacement is a quantity that has both magnitude and direction. So that makes it a vector. Today, we're going to only deal with one-dimensional motion. Everything's going to be along a line. So the sign of the displacement is going to indicate the direction.
Thank you for including these helpful bold or vector arrows to indicate that this is a vector.
Like I said, the sign will indicate the direction. So we'll just omit the vector arrows. But yeah, usually vectors that point to the right will be positive and vectors that point to the left will be negative. But you can, choose it whichever way you want. Let's do the first example. A person walks 30 meters west, then 20 meters east. Determine the person's displacement and the total distance traveled. Is the displacement the same as the total distance traveled? So let's start by drawing a little picture. I'm going to call the initial position of this guy 0. This guy moved 30 meters west, so that's 30 meters to the left, so that's negative 30. And then he moved 20 meters east, so negative 10 is where this guy landed. So like this. So this is x1 right here. This is the initial position, and the final position, x2 right here, negative 10. First thing we need to do is find displacement. So displacement is delta x. So it's x2, so negative 10 meters minus x1, so minus 0 meters. So that is negative 10 meters. Okay, so that's the displacement. So this guy landed 10 meters to the left of where he started. That's what we're basically saying.
You went from west and east to negative and now left.
Yes.
What's the idea?
Well, the sign is all that matters. The negative direction. So it's 10 meters in the negative direction. You can call that left, you can call that west, whatever your heart desires. Now we have to determine the total distance traveled. So what do you guys think we need to do for that?
You defined displacement, but you didn't define distance.
Well, distance is just the total length that you traveled. So direction does not matter for
Right, if
distance.
you were to add those two distances up, it would be 50.
You're right.
Um,
That's the distance. Exactly. So it traveled 30 meters to the left and 20 meters to the right. So the total distance is just 30 meters plus 20 meters, which is 50 meters. So now the $1,000,000 question is the displacement the same as the total distance traveled?
no,
Exactly. It's not the same thing. Some people think displacement is like a synonym to distance, but it's not the same thing. So you can see displacement cares about direction. So displacement could be positive, negative, or 0. So like I said, negative if it's moving usually to the left, and then positive if it's moving usually to the right. But distance is always greater than or equal to 0. Doesn't care about which direction you moved in. It just cares how far you went. Okay, so now that we understand displacement and distance, we can now talk about average speed and average velocity. In everyday language, speed and velocity are used interchangeably, but in physics, there's an important difference between these two terms. Average speed is the total distance traveled divided by the time it takes to travel this distance. So I'm using R for average speed, and D is the distance, and delta T is the time elapsed. So it's
Nick,
yes.
what kind of psychopath uses R for average speed?
What do you want me to use?
Literally anything else. Like R?
Well,
R, are you kidding me?
okay, I know it looks weird, but R was used in distance equals rate times time. Remember this formula? R was the average speed there. This is like from algebra. I think,
So R stands for rate?
yeah, the R is, think of it as rates.
I mean, I think whatever works,
Thank you. Thank you.
This is fake news.
But yeah, we're gonna stick with R. So you're gonna have to deal with it a little bit. So average speed is distance over the time elapsed. Speed is a scalar, so doesn't care about direction. You know, just like distance didn't care about direction, like average speed is not going to care about direction. So speed is always going to be greater than or equal to 0. On the other hand, average velocity, it's displacement divided by the time interval during which the displacement occurred. Sometimes you can see like v average for average velocity, and sometimes you see v bar for average velocity. So I'm probably gonna use v average more. And since we have displacement in the numerator and displacement is a vector, that means velocity is also going to be a vector. So velocity has both a magnitude of how fast the object is moving and also the direction in which it is moving. So it can be positive or negative or 0. All right, so let's do an example. So we have the same situation as last time. So a person's walking 30 meters west and 20 meters east. And suppose this walk took 50 seconds to complete. Determine the person's average speed and average velocity. Is the average speed the same as the average velocity? So average speed, that's R, and it's distance divided by the time it took to travel that distance. So the distance, we did that in the last problem. The same situation, so the distance is going to be the same, 50 meters. And the time it took is 50 seconds. So divided by 50 seconds. So that's 1 meter per second for the average speed. And for the average velocity, so that's v average, that's displacement over time. So delta x over delta t. So displacement, again, we found that earlier. That's negative 10 meters. And it took 50 seconds still. So negative 10 over 50, that's negative 0.2 meters per second. Is the average speed the same as the average velocity?
Using my years of mathematical expertise, I'm going to make a conjecture that 1 is not equal to negative 0.2.
You're right. The average speed is not the same as the average velocity. So no, R does not equal the average. Does anyone have any questions on displacement, distance, average speed, average velocity? So let's.
When are speed and average velocity the same?
Ooh, that would happen when the distance is the same as the displacement. If the displacement and the distance are the same, like basically the object is moving in one direction and it's not like turning around, then yeah, the distance will be the same as the displacement, and then you'll have the same value for average speed and average velocity. That's a really good question.
Thank you. Thank you.
So let's do another example. So you're going to work at a constant 50 miles per hour and return home at a constant 30 miles per hour. The trips together take 2 hours. What is your average speed for the entire trip? Without doing any heavy duty math, what does your gut tell you the answer should be? You're going 50 miles per hour to work, and then you're going 30 miles per hour back home. What do you think the average speed would be?
Using an advanced mathematical formula, we can add one entry to the second entry and divide by 2.
And what would that get you?
40.
Yeah, so you might think, oh, I'm just going to average the speeds, and that will give me my average speed of
Right.
40 miles per hour. But That would actually be the wrong answer. It's not 40 miles per hour. And the reason why is because you spent more time traveling 30 miles per hour since you're moving slower. It's not just going to be a simple average.
You don't spend the same amount of time on the return journey as the going to work journey.
Exactly.
Let's to trust our gut.
Yeah. Sometimes the gut can be wrong. So, what do we have to do since we can't just take an average? We have to go back to our definition of average speed because we can't go wrong with that. I'm going to call the average speed going to work R1. So R1 is the distance. So let's say it travels D distance to go to work, and that takes time T1 to go to work. So this is what we're dealing with for the average speed going to work. And for the average speed going back home, I'm going to call that R2. And again, it travels the same distance and it takes time T2 to do that. And there's another piece of information we have. The trips together take 2 hours. So that means T1 plus T2 is going to equal 2 hours. So we don't know the distance from work to home and home to work. We don't know the time it took for each trip. We just know the total is 2 hours. So we got three unknowns. We don't know D, we don't know T1, we don't know T2. And we got three equations. So can we solve this? Yes, we can. Since we don't know distance, there's a couple ways you can solve this. What I'm going to do is I'm going to take the ratio of R2 to R1 and the distances will cancel. So R2 divided by R1. So that's distance over T2 divided by distance over T1. So these distances right here, this one's in the numerator and this is like in the denominator. So it's going to cancel. And if you do keep change flip, like the T1 will go to the numerator. So it'll be T1 over T2. So this is good. Now we have two equations with only T1 and T2 in it. Because we know R1 and R2. R2 is going back home, so that's 30 miles per hour. And R1 is going to work, so that's 50 miles per hour. So 30 over 50, that's 0.6. And I'll multiply both sides by T2, and you'll get T1 equals 0.6 T2, because this is 0.6. Okay, so I can do some substitution here. So T1, replace it with 0.6 T2. And we can solve for T2 now because it's the only unknown in the equation. So this is 1 T2, so 1 plus 0.6 is 1.6 T2, and that equals 2 hours. And if you divide by 1.6, you'll get T2 is 1.25 hours. So the average speed of the entire trip, we're going to call that R. What's the formula for average speed of the whole trip? Because we have distance over time. So the total distance traveled for the entire trip is 2D. This guy traveled D to go to work and then D to go back home. So the total distance traveled is 2D. So the average speed of the entire trip is 2D divided by the time it took, which is T1 plus T2. Let's do that.
We know the total time is 2 hours. That's given in the problem.
Exactly. So the distance, we can just rearrange one of these equations. Since I know T2, I'm going to go with this equation. So D is just R2 times T2 if you rearrange it. So I'm going to replace D right here with R2 times T2. So we have everything. So I just need to plug it all in. We got 2 times R2, which is 30 miles per hour. So T2, 1.25 hours. And the total time, T1 plus T2, that's 2 hours. So you can see the hours cancel, and you're just left with miles per hour for the units, which is good because we're dealing with average speed. And also the 2's here cancel. So it's just really 30 times 1.25, which is 37.5. Like I said, since we can't just take the average because the time to go to work is different from the time to go home, we have to revert back to our definition of average speed.
Right. Okay.
There's a formula here. V average is V1 plus V2 divided by 2. It's the same idea for speed. You can say R equals R1 plus R2 divided by 2. But that's only true for constant acceleration. Like I said, it's only true for when the time one way equals the time the other way. But if the problem says constant acceleration, then you can just take the average. That's fine. So we'll see that later on.
Yeah, there's no way you get constant acceleration in the example 3 in real life.
Yeah, the acceleration is not constant for this one because you have like two discrete speeds that you're moving at for the whole trip.
You go to work at a constant 50 miles per hour. So you didn't get out of the driveway and like start from rest. You started at 50 miles per hour. And then you crashed into the work building at 50 miles per hour. That's kind of what you're implying with the wording here.
Pretty much, yeah. And then it changed to 30. Since it's like discontinuous, like discrete speeds we're going, this is not a constant acceleration.
We're not taking into account how long the workday was. Does that include in the time that it takes?
Nope, it's just the time it took to drive, which is actually pretty sad. 2 hours to go to work and come back home.
Yeah.
In LA, 2 hours, that's like traveling 8 miles total on the freeway. So I understand. So we talked a lot about average values, but how can we find the velocity at an instant in time? To determine the velocity at some instant, we have to study like a small time interval near that instant. So as the time interval becomes smaller and smaller, basically as delta t approaches 0, this average velocity over that time interval is going to approach the exact velocity at that time. So this is called instantaneous velocity. So instantaneous velocity is the velocity of an object at some instant or at some specific point in the object's path. So it's not an average over some time interval. So we're letting the time interval go to 0, and the average velocity will approach the instantaneous velocity, which I'm calling v. The great thing is that instantaneous speed is always equal to the magnitude of the instantaneous velocity. So you just take the absolute value of the instantaneous velocity, you get the instantaneous speed. This is because the distance traveled and the magnitude of the displacement is going to be the same when the change in time is infinitesimally small. And by the way, for the rest of the lesson, and even for future lessons, when I use the term velocity, I'm referring to instantaneous velocity. But when I'm talking about average velocity, I will make it clear by including the word average. So let's do example 4 now. So we have a car is stopped at a traffic light. It then travels along a straight road such that its distance from the light is given by this right here. Calculate the average velocity of the car for the time interval t equals 0 to t equals 10 seconds. So average velocity, we have to go back to our definition. The average velocity is displacement, so x2 minus x1 divided by the change in time, so t2 minus t1. It says that this is actually the distance, but the problem is that we're dealing with velocity, so we care about displacement. We're not really using distance here. But why does it not really matter for this problem? The car is only moving in one direction. It's not like changing direction, it's not turning around. So the displacement and the distance are the same thing pretty much. The magnitude of displacement is going to be the same as the distance. So for this problem, distance and displacement, it's kind of the same thing. So you don't have to worry about it too much. Since again, we're only moving in one direction. So x2 minus x1 over t2 minus t1. So this is a graph right here of this function, 0.5 t squared plus 1.5 t. And graphically, what does x2 minus x1 divided by t2 minus t1 represent? Does that remind you of something graphically? Like something like a y2 minus y1,
Yeah.
x2 minus x1 situation?
It is the slope of the secant line.
Exactly.
Seek what line?
The secant line. Yep.
Oh, what's
What
that?
did I say?
That's what I heard. But basically, it's a line going from T1 X1 right here to T2 X2. So it's this line. That's the secant line. And the slope of that line, it just X2 minus X1 divided by T2 minus T1, right? Because this is T2 X2. This is T1 X1. So if you use the slope formula, you're going to get this for the slope of that red line. All right, so graphically, that's what we're doing. We're finding the slope of this line going through these 2 points. That's why it's called the secant line. It's going through those 2 points. So the slope of this line is the average velocity. The average velocity specifically from 0 to 10 seconds. If you draw the secant line going from here to, let's say, here, if you draw that line, the slope of that line will give you the average velocity from 0 to 6 seconds. But x2, that's x at 10 seconds. So you can plug in 10 into the function, but you could also just look at the graph and see that that's 65 meters.
Cheating using the graph. You're not always going to get a graph.
I just want to show the graph so you can see graphically what's happening. But
I appreciate this. This is faster than plugging in x of 10 minus x of 0 and doing all the calculations, which is what I was afraid you would do.
oh no, no. And then x1 it's 0. T2, the final time is 10 seconds, and the initial time is 0 seconds. So we basically have 65 divided by 10. So the average velocity is going to be 6.5 meters per second. So this is an average value. The car didn't travel 6.5 meters per second at every moment because it initially started off going 0 meters per second because it was at rest, it was at a traffic light. And then, it starts to speed up. So the velocity changes with time. So, what if I want to find the instantaneous velocity at t equals 3 seconds? Like at this instant, I want to figure out the velocity. Does anyone have any idea how I would do that?
It is dx dt, which is to say the derivative of x with respect to t evaluated at t equals 3. You could also write that as x prime of 3.
That's right. And what is that graphically?
That is the slope of the tangent line at t equals 3.
Exactly. So t equals 3, that's right there. Draw a tangent line going through that point, and the slope of that line is the instantaneous velocity at t equals 3. You need calculus to find the slope of that line. So we have to take derivatives. Like it says right here, velocity is the derivative of position with respect to time. Even though this is a distance function, like I said, position and distance are the same thing because the car is moving in one direction.
In this problem, they're the same.
Yeah, in this problem. So the velocity function is the derivative x prime of t. What is the derivative of this function here?
No, I think Pschilli should do it.
Sure, what's the derivative of this with respect to t?
They're just kind of some magical derivative rules that you can use. And so the magical rule, when you have a coefficient times some power of the variable that you're taking the derivative of, is to take its exponent down, multiply the coefficient by the exponent, and then take that product and multiply it by that same variable, but raised now to one less power than it previously was. So if it was 2, now you raise it to 1. And so here you would have 2 times 0.5 times t.
Exactly.
Now, random guy, how the heck do you do it when t is only raised to the first?
Well, my friend, when t is raised to the first power, you can still subtract 1 and it becomes t to the 0 power, which would be 1, and therefore a constant times the variable. The derivative will just be the coefficient.
Yeah, so when you take the derivative of this, the 2 goes to the front and it becomes t to the power of 1. So you just have 2 times 0.5, which is 1, and then times t. So it's just t for the first term. And then for 1.5t, this becomes, you move the 1 to the front, subtract 1 from the exponent, and you get 1.5 times t to the power of 0, which is just 1.5. So it's t plus 1.5. That's the derivative of this distance function. And we want the instantaneous velocity at t equals 3. So I'm going to plug in 3 seconds into this function. So you have 3.0 plus 1.5. So at 3 seconds, the velocity is 4.5 meters per second.
Very informative. Thank you.
Of course. To sum up, for any position versus time graph, the average velocity between 2 points is the slope of the secant line connecting them, and the instantaneous velocity at a specific time is the slope of the tangent line to the graph at that point.
Actually, to sum up, that would not be correct. To sum up, you would get the integral.
Oh my god. Yeah, that's true. Next, example 5. So a cat is walking in a straight line. You make measurements of this cat's motion and construct a graph of the cat's velocity as a function of time. What distance does the cat move during the first 3 seconds? This is the velocity. We know the velocity, but how do we go from velocity to distance? Let's go back to the definition of average velocity. Part A, we know average velocity is displacement over time. And there's no distance in this formula, and we're trying to find distance. But that's okay because in the first 3 seconds, the cat is only moving in one direction. Since the velocity is positive in the first 3 seconds, let's call the right positive, then it's just moving to the right the whole time. So the displacement and the distance, it's the same thing for this time interval in this problem. So I can just rearrange this and, multiply by delta t, and I can say distance is v average times delta t. Okay? And is the acceleration constant in this problem?
Acceleration is the slope of the velocity graph, and the slope of the velocity graph seems to be constant.
Exactly.
Right. It's a straight line.
Exactly. The velocity is a linear function here. So acceleration is just going to be a number. So since acceleration is constant, remember this thing we avoided earlier? We can literally just take the average of the initial and the final velocities, and that will give you the average velocity because it's a line. This is v1 right here, and this is v2. If I add that up and divide by 2, I'll get my average velocity right here because it's a line. You can do that. If this was curvy, you can't just do v1 plus v2 divided by 2. So the average velocity in this case, again, since it's a line, we can do v1 plus v2 divided by 2. And then we have that times delta t. What does this look like graphically? This looks like a certain formula to me. It looks like the area of a trapezoid, right? Because the area of a trapezoid is the average of the bases times the height. Like, let's say this is the trapezoid. This is the one base, this is the other base, and this is the height of the trapezoid. If you take the average of the bases, multiply it by the height, you'll get the area of this trapezoid. So this looks like the area of a trapezoid. And
Yeah, the way you drew your trapezoid gave me an aneurysm, like on its side with the height at the bottom.
Well, I purposely drew it like that because it's gonna look like that right now. So we're analyzing this from 0 to 3 seconds. So I'll draw a little line at 3 seconds. This is V1 right here. This is V2, the final velocity at 3 seconds. This is the delta t. The distance is just the area of this trapezoid. It's V1 plus V2 divided by 2 times delta t. So let me shade this in. The area of that trapezoid is going to be the answer to part A. So V1, the initial velocity, we can see is 9 centimeters per second. The final velocity is 3 centimeters per second divided by 2. And the time interval is 3 seconds. All right, so we got 12 divided by 2, that's 6, times the 3, that's 18. And this is going to be in centimeters because we have centimeters per second and we're multiplying by seconds. So this will be 18.0 centimeters. So that's the distance this cat traveled in the first 3 seconds. All right, let's look at part.
Right.
It is moving all to the right. So part B is what distance does the cat move from t equals 0 to t equals 6 seconds? So again, the area under this curve is displacement, and displacement's related to distance. So I just have to find the area under this curve, above or below it, from 0 to 6 seconds. So we already did 0 to 3 seconds, so let's just find the rest of the area. So we have to look at this area here and this area here.
Nice visual. Thank you.
Yeah, for sure. We already have this area. We found that's 18 centimeters. And let's add these areas now. So it's a triangle. So how do you find the area of a triangle?
1/2 base times height.
Exactly. The height is 3. We have base is 1.5. So it's 1/2 times the 3 centimeters per second times the 1.5 seconds. So that's this triangle right here. And normally we would subtract this area here because it's below the t-axis. Because over here, the velocity is negative. The cat is moving backwards after 4.5 seconds. But the distance is still increasing. The distance doesn't care if the cat's moving forward or backwards. It doesn't care about direction. So if the problem said find the displacement, I would have subtracted this area. But since we're finding distance, I'm going to add this area. And these triangles have the same base and height, 3 here and then 1.5 here. So I can just do 2 times this area here. All right. And again, area under the curve of a velocity versus time graph is displacement. But since we're trying to find distance, normally we would subtract this area, but we're going to add it. So the 2 and the 1/2 here will cancel. So you have 18 plus 3 times 1.5. You will get 22.5 centimeters. Okay. So on a velocity versus time graph, the area under the curve between 2 times represents the displacement over that interval. So now that we talked about velocity and all that stuff, we can now talk about acceleration. So average acceleration, this is the change in velocity divided by the time taken to make this change. So it's delta v divided by delta t. And since velocity is a vector, velocity cares about direction, so does acceleration. So acceleration could be positive, negative, it could be 0. All right, so let's take a look at this problem here. We have a bus traveling at 18 meters per second and it sees a red light ahead. The driver applies the brakes, causing the bus to slow down with an average acceleration of negative 1.8 meters per second squared. After 3 seconds, the driver realizes the light turned green and immediately releases the brakes, allowing the bus to coast at the speed it has reached by then. How fast is the bus moving at the moment the driver releases the brakes? Okay, very interesting problem. We're trying to figure out how fast. So we want final velocity. They give us average acceleration. They give us a time. They give us initial velocity. So looks like this formula will be pretty useful. We have average acceleration, we have initial velocity, we have the change in time. We can find the final velocity. So let's use this formula. Average acceleration is v2 minus v1 divided by the change in time. And we want v2. How fast is the bus moving when the driver releases the brakes? So let's rearrange. So I'm going to multiply both sides by delta t, and I'll get v2 minus v1 is average acceleration times delta t. And we want v2, so I'm going to add v1 to both sides. So I get this plus v1. So average acceleration, negative 1.8. And accelerations in units of meters per second squared. The time interval, 3 seconds. Initial velocity, 18 meters per second. So if you do all the math, you'll get that the final velocity is 12.6 meters per second.
It's weird hearing you say if you do all the math, because normally you do all the math.
That's true.
When you're doing like a calculus problem, do a complicated integral, and then at the end you'll just be like, okay, so you cancel this with that, and don't forget to carry the two. That's the way you are.
Yeah. But
It's physics.
I'm different now. It's physics. All right. So that's the velocity of the bus when the guy releases the brakes. And it says, how much longer will it take the bus to come to a full stop if the brakes are reapplied immediately with the same average acceleration of negative 1.8 meters per second squared? So we're given average acceleration, so we're going to use the average acceleration definition. This is the velocity it's going when the brakes are reapplied. So it's starting off with this velocity now, and it's going to go down to 0. So we're going to call that v3. So the final velocity, v3, which is 0, minus v2, divided by the time it takes for that to happen, which I'll call delta t prime. We want delta t prime. It's asking how much longer. So I can multiply by delta t prime on both sides and divide by the average acceleration. And you'll get delta t prime is v3 minus v2 divided by average acceleration. So v3, that's the final velocity, which is 0 because it's coming to a complete stop, minus the initial. So the initial now is the 12.6, and the acceleration is the same. The average acceleration is still negative 1.8 meters per second squared. So if you divide, you'll get that the time it took to come to a full stop is 7 seconds. All right. So we talked about average acceleration. Now we can talk about instantaneous acceleration. So this is the acceleration of an object at an instant or at a specific point in an object's path. So just like we did with instantaneous velocity, we're going to let the time interval go to 0, and the average acceleration will approach the instantaneous acceleration. And you can see this is the definition of a derivative. So it's a derivative of velocity with respect to time. So a race car starts from rest and travels east along a straight and level track. For the first 8 seconds of the car's motion, the eastward component of the car's velocity is given by this function here. What is the average acceleration of the car for the time interval t equals 0 to t equals 5 seconds?
I mean, this is pretty much the exact same problem as example 4, but now we're like doing the derivative of the last problem. Yeah, the average is just going to be the slope of the secant line, et cetera, et cetera.
Exactly. So average acceleration, we know the formula is v2 minus v1 over t2 minus t1. So this is just slope. It's y2 minus y1 over x2 minus x1. It's the slope of this secant line specifically from 0 to 5 seconds. So it's from here to here. All right, so the slope of that line will give you the average acceleration. Again, you can plug in 5 seconds here, but you could also just look at the graph. So you can see the velocity is 10 meters per second at the end, and it's initially 0. So 10 meters per second minus 0 meters per second over the 5-second time interval. So 5.0 seconds minus 0 seconds. Basically, we have 10 divided by 5, and that's just 2. And this is meters per second, so it's meters per second squared. So 2.0 meters per second squared. All right?
I mean, this is just an Algebra 1 problem.
Yeah. And now, what is the acceleration of the car when v is 19.6 meters per second?
Oh, goody, a calculus problem.
Yeah, remember, when I say acceleration, I really mean instantaneous acceleration. So we want the acceleration at the instant v is 19.6. So, like right here. You can
Are
kind
we
of
guessing it from the graph, or?
we can guess it from the graph, but let's actually find it exactly. It'll be quick. So we know v, I'll ignore the units for now. V is basically 0.4 t squared. And v, we know it's 19.6. So let's figure out what time the velocity is 19.6. So I'm going to divide by 0.4, and you actually get 49. I did that on purpose. Take the square root, and you get t is 7.0 seconds. So yeah, you could have eyeballed that, but we found it exactly. It turns out it's exactly 7 seconds. Think of this problem as saying, what's the acceleration at 7 seconds now? So acceleration is the derivative of velocity with respect to time. So a of t is v prime of t. What's the derivative of 0.4 t squared?
We can use the handy dandy power rule and bring down the 2 and reduce the exponent, and therefore it is 0.8 t.
Exactly. I'll put the units like this. That's the derivative. So we just need to plug in 7 seconds. That's why we found t, so we can plug that in.
V prime of 7.
I was just going to say a of 7, but yeah.
Good to show that it's all the same.
Yeah. So we basically have 0.8 times 7, so that's 5.6. And we have meters per second cubed times seconds, so that becomes meters per second squared. So 5.6 meters per second squared. Okay, so that's average acceleration, instantaneous acceleration. And graphically, what we found here is the slope of the tangent line. For part B, we really found the slope of the tangent line at 7 seconds. Found the slope of this line. That's what a derivative is at a point.
This all seems terribly familiar.
Yes, very similar to a couple examples ago. All right, so just to summarize, for any velocity versus time graph, the average acceleration between 2 points is the slope of the secant line connecting them, and the instantaneous acceleration at a specific time is the slope of the tangent line to the graph at that point. All right, last example. A rocket is launched vertically upward from the surface of the Earth with an initial velocity of 105 meters per second. You make measurements of the rocket's motion and construct a graph of its vertical acceleration as a function of time for the first 10 seconds. What is the rocket's velocity at t equals 10 seconds? So we want velocity at this point here at 10 seconds.
I do want that, yes.
And we're given data on acceleration. I need something that relates acceleration and velocity, so I'm going to use average acceleration is delta v over delta t. And we're interested in velocity, so I'm going to multiply both sides by delta t. So average acceleration times delta t. So the average acceleration, since acceleration is linear, I can just do a1 plus a2 divided by 2. And that will give me average acceleration. A1 right here is 0, so we're just doing a2 divided by 2, really. We're doing 1/2 a2, which is acceleration at 10 seconds, times delta t. What does this look like graphically? 1/2 a of 10 delta t?
Well, that sure looks like a triangle if I've ever seen one.
Yeah, this is the area of a triangle. It's 1/2 base times height. We're basically finding the area under this curve.
I find it fascinating that this all relates to the area of different shapes It's very interesting how that all connects.
Yeah, that's why I'm giving you the graph. Not every physics problem is going to give you a graph, but
It's a help visual.
yeah, I'm trying to help you guys visualize that. I wrote it right here in red. On an acceleration versus time graph, the area under the curve between two times represents the change in velocity over that interval. So this will give us the change in velocity, the area right there, that green shaded area. So acceleration at 10 seconds is 55 meters per second squared. And the time is 10 seconds. So I just have to plug everything in. And that's going to be 275 meters per second. Is that it? Is that what we wanted? The area under the curve is the change in velocity, but I want the velocity at 10 seconds. Change in velocity, let me move this here. It's final minus initial velocity.
Well, we know the initial was like 105, right?
Yeah, right here. Initial velocity is 105 meters per second. So
Yeah, a good problem solving technique is to look at what you're given in the problem and figure out why they gave that to you.
exactly. Most of the time, you're going to use every piece of information in the problem, unless your professor's trying to trick you and puts information that's useless in the problem. So, change in velocity is v2 minus v1. I added v1 to both sides. We know v1 is 105 meters per second. So, the final velocity, the velocity at 10 seconds, is going to be 380 meters per second.
It ain't rocket science, people.
Exactly. That is it for today. Thank you to everybody.
Very informative.
Yeah, for sure. Thank you.
Thank you so much, Nick.
I'm glad you found it useful.
Nick, thank you so much for the calculus lessons. I'm sorry random guy berated you so much.
No worries. I'm used to it.
He is used to it.
Uh,
I took physics a long time ago, but I'm glad to be taking these lessons again.
Yeah.
but don't forget to like, subscribe, and comment. And I'll see you guys in the next video. All right.
Yeah, next video will be on quantum mechanics, so stay tuned.
Yep.
Bye.
Pschilli signing off. Adios.